Hi everyone, I hope you're doing well. In this video, I will talk about 10 additional questions that are commonly asked in Gen AI interviews. And there is no surprise that our next question is about RAG, which stands for Retrieval Augmented Generation. I can assure you guys that nowadays RAG became ubiquitous in industrial life. And if you are hitting an interview for a Gen AI job, be sure that you will be asked this question. And I've already talked about RAG, but this is an occasion to see it again. So this is the whole pipeline for Retrieval Augmented Generation. But before stepping in RAG pipeline, let me explain to you what is RAG. So RAG, which is Retrieval Augmented Generation, as its name indicates, it permits large language models to generate answers based on additional information retrieved from external data sources. Here in this pipeline, our external data sources are these documents. They can be any type of document that will be processed later. Once we have this data, we proceed to chunking that I explained in my previous video. This results in chunks of documents which will be passed to an embedding model where they will be converted into vectors representations like what you see here. These vectors will be stored in what we call a vector store that will be used in the process to retrieve relevant information to answer a user's question. So let's see an example from real life to make this clearer. Let's say we have a user query. This query will be embedded using the same embedding model as the one used to embed the chunks. A similarity search will be done to look for the documents, the most relevant document to answer to the user query. Here we have 4, which is the number of relevant documents, and it's a parameter that we can fix in the retriever. Once we have these relevant documents, we inject the whole information in a prompt. As an example of prompt, we have answered this query based on the following context, and we replace query by our query and the context by the returned or retrieved documents that will be relevant to answer to user query. Once we have our prompt, we inject it in an LLM, which will process the whole information to return the final answer. This is why it's called Retrieval Augmented Generation. Here I listed different RAG steps. I will put the document in the video description, guys, with all the sources that I used to create it. Our next question is about top K and top P sampling. To explain this, I will take the same example that I took to explain RAG. So let's say that we have in our vector store, we have 100 documents. If we fix K equals to 20, our retrieval step will return 20 documents without having any consideration related to the probability. Of course, the 20 returned documents will be the most relevant documents in terms of probability compared to the whole set of documents in the vector store, but only the 20 or the K most relevant documents will be returned in the research. On the other hand, in the top P sampling, only documents with a probability that exceeds a certain threshold will be returned. For example, if we fix the threshold to 0.8, only the documents with a probability greater than 0.8 will be returned. The risk here is that if no document has probability higher to 0.8, you will not find any document after the retrieval step. This is why it's more secure if you really need to return documents after the retrieval step to use top K sampling instead. Our next question is about encoders and decoders. As their names indicate, encoders encode or process input sequences. Like here we have I'm a student. Encoders convert the sequence into abstract representations, and decoders take these representations to generate a output sequence. And starting from the second token, decoders take the encoder's outputs plus prior tokens like je in this case. And this takes us directly to sequence-to-sequence models, which use encoders and decoders to transform input sequences into output sequences, generally of different lengths. As the example that we've just seen, sec-to-sec applications include machine translation, text summarization, chatbots, and so on. Let's see this in a live machine translation example. I will put the link to the example in the video description, guys. So here we have a sentence, je suis étudiant, which is in French, that we want to translate it into English. As you see here, tokens will be passed one by one to encoders. Each encoder takes the previous hidden state, which is the hidden state of the previous encoder, with the actual token to generate a new hidden state. I will not go into details about hidden states, guys, but let me know if you need more details on this and I can create a video about that. Now, once we have the three hidden states ready, they will be injected in a set of decoders. As you see here, the first decoder generated the word I, knowing that our example is je suis étudiant in French, which is I am a student in English. So the first generated token is I. This token will be given to the next decoder jointly with hidden states from the encoding stage, and the same will be done for the other decoders to generate the final sequence. The next question is about transformers and how this architecture improved traditional sec-to-sec models. This is existential question, guys, because the appearance of transformers architecture, guys, in 2017 was a revolution in deep learning and NLP fields. This is because transformers overcome neural networks limitations that we have for decades. And this is thanks to three main innovations. The first one is parallel processing. Self-attention enables simultaneous token processing by doing calculations between each token and the other tokens of the sequence. We have long range dependencies because each token is in a direct connection with any other token in the sequence, regardless their distance, and this enables to capture distant token relationships. And as calculations are done in parallel, so in some way we lose the position of each token relative to the other ones, but this is overcome thanks to positional encoding, which gives the model information about the position of each token in the sequence. Don't worry, guys, if this is still not much clear, it will be clearer in the next question, where I will give an example where self-attention is applied. So to understand self-attention, let's take this sentence as an example. The animal didn't cross the street because it was too tired. Here the problem is it's very easy for a human to understand that the word it refers to animal, but it's not that simple to an algorithm. And this is why self-attention is a game changer, because it makes the model able to associate it with animal. This is done because when processing each word, self-attention permits to look at all the words in the sequence, which leads to a better encoding and understanding of the actual word. And this is illustrated in this image. So we have our same example. The animal didn't cross the street because it was too tired. When processing the word it, we weigh the significance of each word in the sequence related to this actual word, and we see that the animal, the group of words, the animal, has a higher weight than the word street. That's why the model understands that it refers to the animal and not to street. And as we have self-attention, we also have masked self-attention. To explain this, I will take this sentence of 4 words. Robot must obey orders. In a language modeling scenario, this sentence will be processed in 4 steps. So we have our example here. Here we are considering each word as a token. So we are not tokenizing the words here. It's not the focus of the example. As you see here, in each step, we keep first words of the sequence seen and we mask the rest of the sequence. So here we give a robot to the model and we mask the other ones. And labels here are the words that the model is supposed to predict. So when we give the model robot, the model is supposed to predict must, which is the next word. Once we have must, the model is supposed to predict obey, which is the next word of this sequence. And based on the number of words given to the model, its attention will be split into these given words. For example, when we are processing the first word, the whole attention will be given to that word. In the second step, the attention will be split on the two words, which are robot, must. For example, 48% of its attention will be given to robot and 52% will be given to must. And this leads us to this kind of matrices called masked scores matrix. The next question is about next sentence prediction. So next sentence prediction is a NLP task used among other tasks to pre-train large language models. The task consists on understanding the relationship between two sentences. So let's say that in our pre-training scenario, we have a set of A and B sentences where the goal is to predict if sentence B is next to A or not. Generally in machine learning, when the set of examples where the sentence B is next to sentence A are called positive examples, the other ones are called negative examples. Generally, to have a good distribution of data, we choose 50% of the examples to be positive, the other half are negative. And for the negative examples, we just need to choose a random sentence and put it next to the sentence A. The task looks very simple, but it has been demonstrated that it's very beneficial for downstream tasks like question answering and natural language inference. Congratulations guys, because you made it till this level of the video. We still only have two last questions. Of course, we can't finish the video without talking about overfitting, which is one of the most seen problems after training large language models. The problem consists on memorizing much information related to training data to an extent that makes the model fail to generalize on unseen data. Many techniques are used to reduce overfitting. Among them, we cite regularization, which consists on adding some penalties to the model's complexity to make it simpler. Dropout is used as well, which consists on disabling or shutting down some neurons from the neural network, which consists on forgetting some learned information. Or last but not least, early stopping can be used as well. And here we are talking about stopping the model training once it attains a certain level of performance. The last question of this video is about LoRa and QLoRa method. LoRa stands for low rank adaptation, and it's a very used method that ensures efficient fine-tuning. This is done thanks to adding low rank matrices, enabling efficient adaptation with minimal memory. On the other hand, QLoRa extends LoRa by applying quantization, which reduces memory more while maintaining the same level of accuracy. This is it guys for today. Thanks for watching and congratulations again for staying to the end of the video. Please don't forget to subscribe to the channel to get notified when I publish more videos like this one. And please don't hesitate to ask me questions on any concept about which I talked so far, and see you next time.